Hello, thanks for joining me for another session about semi-passive water treatment. Here we're going to be talking about what can be treated in things like treatment wetlands, biochemical reactors, and in situ treatment. If you want to know more about those, we'll have some links below. So what can be treated? I'm not going to go into each of those technologies individually because they all treat water through biogeochemical processes. And depending on each of the design, and many of them can have many different designs, you're going to get different treatment efficiencies and capabilities. So I'm going to talk about what can be treated biogeochemically. I'm going to do part of it at a high level on the whiteboard here, and then going to go into a periodic table which is color-coded for some of the reactions after. I think to make it easy on everybody, let's start with what cannot be treated. So then if that's what you're interested in, you can just stop watching this right away. Things that cannot be treated biogeochemically are things that have no redox sensitivity. So that is things like salts. So potassium, salt, chloride, and fluoride. You're not going to treat those well in a semi-passive system, or biologically, I should say. In fact, if you try to treat these in something like a treatment wetland, you're actually going to get a higher concentration of them. You're not going to add in, you're not going to get more load, but because of evaporation, it's going to be a higher concentration. So not good for those types of things. It is good for metals, metalloids. You can co-precipitate them with sulfides into minerals that are really stable, or if you're doing an oxidative process, you could go and co-precipitate with iron or manganese, which is also very effective. So two different pathways depending on what you're trying to treat. Then there's also some things like selenium, uranium, and vanadium that can be directly biologically reduced into a mineral because they're redox sensitive, so really good at those types of things. Cyanides, I say as a plural because I view that as a bit of a family of compounds where you have your SAD and your WAD and free cyanide, that's strong acid dissociable, weak acid dissociable, and free. But then you also have your thiocyanates, your cyanate, cyanite, selenocyanates, so you have a whole group of cyanide type compounds there. Those can be treated in semi-passive treatment systems or also in a heap leach, so you can directly detoxify the heap leach of the cyanides in situ. So in place without having to pump and treat. Organics. Here's some of the tests that are often used to tell if you have organics present. So total organic carbon, dissolved organic carbon, biological or biochemical oxygen demand. And here's a few examples, not exhaustive, but you have your oil, grease, polyaromatic hydrocarbons, PHs, BTEX, which is benzene, toluene, ethylbenzene, and xylene, nitrosamines, and piperazine, and then also naphthenic acid fraction components or compounds, and those are from oil sands and other bituminous compounds. Could include things in here also like, it's not relevant to mining, but a lot of the dry cleaning waste have been treated through these types of things. So a wide range of organics could be included in here. Triethylene glycol used in natural gas dehydration, so many things can be treated that way. And then also nutrients. Oh, before I go to nutrients, because they tie together, I should mention BOD is often discussed in these types of systems from a wastewater perspective, meaning municipal wastewater, which is sewage. So you don't normally see sewage in a mine or oil sands or oil and gas type water. Those are usually treated separately. We're talking really about the organic compounds here that do produce that demand also. Nutrients. So where do nutrients come from in mining? Where is your nitrate, nitrite, ammonia, ammonium coming from? Well, from ANFO. So ammonium nitrate, which is blasting compounds, as well as from the cyanide components if you have cyanides on site. So these can all be treated. I could have put NH4 here also. It's just at the higher, NH3 is more biologically available to microbes for nitrification, whereas the NH4 is more of a plant uptake pathway. So we tend to push it towards a higher pH NH3 for treatment. Phosphorus is present on site often just naturally in an ore body. So sometimes you'll see a little bit or a lot of phosphorus at different sites, and that can be treated as well as total suspended solids. So that's a really wide range. I wrote that by memory, so I hope I didn't miss anything. If I did, we'll put it below in the comments and in the description. A few things I want to touch on that are possibly treatable semi-passively are these ones here. So we have sulfate, acidity, and pesticides. Sulfate, you definitely can reduce sulfate in a semi-passive treatment system or in an active treatment system. You can turn the sulfate to sulfide, as I mentioned, but you're bound stoichiometrically by your metals or what's going to bind to your sulfate or your sulfide when it's done. So you need to think of the stoichiometry of your system, your balance. We'll talk about that in another video, but sulfate is possible, but especially semi-passively, you're probably looking at a small amount, or you're getting into the spectrum of more towards semi-active rather than semi-passive. So more that way, because you need to add something to balance out the sulfate. Same thing with acidity. Reducing systems or anaerobic systems can actually produce alkalinity, which buffers against acidity, or you can add in buffering capacity like limestone into a system, but it's going to be finite. So that's why I said somewhat, adding lime into an open pit, that's pretty passive. You can just dump it in, it's there, you're not managing it day to day. But usually that will have to be replenished unless it's paired with a secondary process. So that's why I put as a, keep an eye on that. And pesticides, we don't usually encounter that in oil and gas and mining, but for example, xylene is, or was, probably still is, licensed as a pesticide in the United States. Probably other places too, I'm just aware of the one. So depending on what concentration your xylene is, it's a pest, or actually an herbicide, I should say. It's an herbicide, so you're gonna wanna watch out for that in terms of a treatment wetland, but you could treat it in a gravel bed reactor. So that will influence what you're going to use for your treatment. Just gonna grab a marker here. Okay. So, of course, we're not saying these things are magic, far from it. These things, treatment systems, are all designable, calculatable. We can model them and predict what they're gonna do. So I wanna make sure I'm not getting taken out of context. I'm not saying that all metals and metalloids, no matter what concentration, can be treated, this is magical. Of course, it's gonna depend on your initial inflow concentration, CI, what your needed outflow concentration is, your CF, and what your flow rate is, as well as, I'll just write it this way, what your area is. So you might have a high flow and all this works, but you don't have enough area for a system, and vice versa. You can mix those around. In addition to that, you also have to pay attention to your total water chemistry. So you might have something that's readily treatable, but the pH is very off and needs at least some intervention actively to make it treatable the rest of it treatable semi-passively. So looking at the total water chemistry in addition to what you need to treat. And then beyond that, you also have things like your periodicity of water flow, temperatures, and available infrastructure, such as, like I said, also area, but infrastructures. So I'm gonna go over now to trying out the periodic table that has the color coding on it, and I'll add that on to this after. So here we have the periodic table of biological water treatment that I was mentioning. I'd like to point out that this is an adaptation of a figure I saw in a paper from 2009. It was by Gusick et al. And I really liked that presentation. They were looking at multiple different types of water treatment. And I thought, this would be really handy to do a new version of this a decade later now, focused on biological water treatment. And we'll include a link to that article below in our write-up, as well as I believe they have a updated article around 2013. And they go into a lot of the different mechanisms. It's quite an interesting paper, so thought we'd share that along, and always want to make sure we give credit where due. So here's our version of a periodic table for biological water treatment. And what we've done is color-coded based on the most commonly seen treatment mechanisms in biological treatment. And by treatment mechanisms, we'll also put a link below for a post we have about transfers and transformations, which explains these actual treatment mechanisms a little bit better. But here you can see, out of the whole periodic table, a lot of these things you just don't see in mining or oil and gas impacted waters needing treatment, like some of the noble gases, for example. So we just highlighted the ones that we commonly see needing treatment and the ways you could treat it. So a lot of them you can see are both blue and green. That means that you could approach their treatment either through reduction and precipitation as a metal sulfide or through oxidative co-precipitation. So you have two different treatment pathways you could pursue there. And others can be directly reduced and treated or combinations of treatment. So I'll leave you to look at this periodic table. It'll also be below in a downloadable link if you want to take a look at that. And thank you very much for your time on this presentation.